Okay, so let's begin. Thanks for coming. Today, well, first of all, let's recall that at the previous lecture, we constructed the continuous functional calculus for normal elements in a C-star algebra. And today, our first goal will be to apply the functional calculus to the study of positive elements in C-star algebras. So suppose that we have a unit of C-star algebra A. A is a unit of C-star algebra. We say that an element of our algebra A is positive if it is self-adjoint and if the spectrum of this element is non-negative. Let's recall that in a general case, the spectrum of a self-adjoint element is real. And if it is non-negative, then we say that our element is positive. Well, maybe it would be more correct to call such elements non-negative, but nevertheless, this is a standard terminology. So let's follow the tradition and call such elements positive elements. Here's a simple example. Suppose that A is the algebra of continuous functions on a compact topological space X. And little a be an element of this algebra, that is a continuous function. Then A is positive in the sense of the previous definition, even only if our function is non-negative at every point. Well, indeed, let's recall that a function is self-adjoint if and only if it is real, and the spectrum of a function is just the set of values of this function. So the spectrum is non-negative if and only if a of x is positive, is non-negative. So morally, positive elements, well, first of all, self-adjoint elements could be considered as non-commutative analogs of real numbers. And the positive elements are non-commutative analogs of non-negative numbers. Let's introduce some notation. The set of all self-adjoint elements of our algebra will be denoted like this. And the set of all positive elements will be denoted in this way. And the following result, the position, describes the basic properties of the set of all positive elements. So first, if little a is a positive element, and lambda is a non-negative real number, then lambda a is also positive. Condition 2, if you take the set of all positive elements and take the intersection with minus the same set, then the intersection is 0. Property 3 says that the set of positive elements is closed in A. And finally, I claim that the sum of two positive elements is also positive. So basically, all these properties mean that the set of all positive elements is a convex closed cone in A. A convex closed cone. Well, now to prove this result, we need a simple lemma. Suppose that A is a unit of C-star algebra. Little a is an element in A, such that the norm of A is less than or equal to 1. Then I claim that this element is positive if and only if it is self-adjoint, and the norm of 1 minus A is less than or equal to 1. So this is a useful characterization of positive elements in terms of in terms of the norm. To prove this result, first of all, let's observe that this result is clear in the case where A is the algebra of continuous functions on a compact topological space. This is clear if A equals C of X. Well, indeed, if A is C of X, then little a is just a function. So it's very elementary to show that a real function, which is whose values are between -1 and 1, is non-negative, if and only if the norm of 1 minus a is less than or equal to 1. So otherwise, our function will be negative at some point. And at the point where it is negative, 1 minus a would be strictly bigger than 1. Okay, so this is a special case where A is the algebra of continuous functions on a compact topological space. Now, in the general case, we do the following trick. We consider the C-star subalgebra of A generated by little a and the identity element. So since our element little a is assumed to be self-adjoint, this algebra is commutative and unital. So we can apply the Gelfand-Nyberg theorem to this algebra. And so we see that it is isomorphic to C of X, where X is a spectrum, the maximal spectrum of this algebra. So everything is reduced to the case where A is C of X. This is a nice application of the Gelfand-Nyberg theorem. Okay, so this completes the proof of the lemma. Now let's prove the proposition. Well, part one is clear from the definition. If little a is self-adjoint and its spectrum is non-negative, then the same is true for lambda a. To prove part two, let's take an element in the intersection of a pose and minus a pose. So what can I say about the spectrum of this element? From the definition of a positive element, we conclude that the spectrum of A is 0. So it is non-negative and non-positive at the same time. So the spectrum is 0. And so the spectral radius is also 0. But our element is self-adjoint. And we know that for self-adjoint elements, the spectral radius equals the norm. And so we conclude that A is 0. Now to prove properties 3 and 4, we apply our lemma. So by the lemma, we have the following equality. The intersection of the positive cone with the closed unit ball of A is the same as the intersection of the set of all self-adjoint elements with the unit ball and with the set of those elements in A for which 1 minus the norm of 1 minus A is less than or equal to 1. Well, here I denote by bold B the unit ball. So this equality is basically equivalent. This equality is equivalent to our lemma. And it does the job because, what can we say about the right-hand side of this formula? So we have here two balls, two closed balls. So two closed balls, all of them are convex. The set of self-adjoint elements is a real vector subspace. And it's also easy to see that the set of self-adjoint elements is closed. So the right-hand side of this equality is a convex closed set. This implies that the intersection of the positive cone with the unit ball is closed and convex. And this readily implies both 3 and 4. Because, since the intersection of the positive cone with the unit ball is closed, it readily follows that the positive cone is itself closed. Because if you have a sequence in the positive cone, a convergent sequence, we can multiply all members of the sequence by a suitable little number, so that the resulting sequence will be in the unit ball. And so since the intersection with the unit ball is closed, we conclude that the set of positive elements is closed. And since it is convex, to show that A plus B is positive, the sum of two positive elements is positive, we simply observe that A plus B is 2 multiplied by A plus B over 2. So A plus B over 2 is positive by the convexity argument, and when we multiply it by a positive number, we get a positive element. So this completes the proof of our proposition.
Sorry, could we prove the lemma using spectral radius, like the part 2 of the proposition?
You mean avoiding the Gelfand-Naimark theorem?
Yes.
Well, maybe. Maybe, but at the moment I'm not sure. Well, let's think about this at home. So to use it, if we take probably, but I'm not sure.
Okay, thank you.
Another useful property of positive elements is that each such element has a unique positive square root. So let's introduce some notation. If let A is a positive element of our algebra, then we denote by the square root of A, the square root of A. That is the result of applying to A the square root function. Here f of t is the square root of t. This is a continuous function defined on the non-negative half line. So we apply just the functional calculus to our element, and the result will be denoted by the square root of A. And we have the following result. For each positive element of our algebra, the square root of A is a unique positive element. Such that the square of this element equals A. Okay, so let's prove this result. Well, first of all, why is it positive? First of all, let's observe that this element is self-adjoint, because the square root function is real on the spectrum of A. And the functional calculus is a star homomorphism, so it takes self-adjoint elements to self-adjoint elements. In other words, the functional calculus takes real functions to self-adjoint elements. And so the square root of A is self-adjoint. And to show that the spectrum of A is non-negative, the spectrum of the square root of A is non-negative, we simply recall the spectral mapping theorem. So the spectral mapping theorem tells us that the spectrum of f of A is f of the spectrum of A. And since the square root is a non-negative function, we conclude that the spectrum of the square root of A is non-negative. So this implies that our element is positive. And it's clear from the superposition property that the square of this element equals A. So let's recall that the superposition property of the functional calculus tells us that if we have two functions, f and g, and if we first apply f and then g to an element A, then the result will be the composition, the superposition of g and f applied to A. And this implies this identity. Now we have to prove that such an element is unique. Let's prove the uniqueness of the positive square root. So suppose that b, little b, is a positive element in our algebra, such that b squared equals A. Again, we apply the superposition property. And we see that b equals the square root of b squared. Of course, here the positivity of b is essential. So on the positive half line, the composition of the square function and the square root function is the identity map. And so we have this formula. And so b squared is a, so this is the square root of a. And we see that such an element b is unique. And this completes the proof. Okay, here's another useful property of positive elements. One more proposition. So as before, we assume that A is a unital C-star algebra. I claim that for each element, literally for each self-adjoint element in our algebra, there exists a unique pair A plus and A minus of positive elements such that A equals A plus minus A minus, and the product of A plus and A minus is 0. Well, before we prove this proposition, let's observe that for C of x, for the algebra of continuous functions on a compact Hausdorff topological space, this result is more or less obvious. Well, here's the picture. If little a is a function, so this is the graph of our function. It is assumed to be real because it is self-adjoint. Well, and if this is the graph of our function, then, oops, I'm sorry. So this is the graph of our function, and this is the graph of A plus. So basically, A plus is the maximum of A and 0. And A minus is uniquely determined by A and A plus. Okay, now let's prove this result in the general case for an arbitrary unital C-star algebra. To prove the existence of such a pair, we again apply the functional calculus. So we consider the following two functions. They will be denoted by t plus and t minus. So they are defined on the real line, and they are non-negative. And instead of writing the formulas, I'll just draw pictures which explain what t plus and t minus are. So this is the graph of t plus. And this is the graph of t minus. So I hope it's clear from the pictures what the functions are. Now I claim that the elements, if you define A plus as t plus applied to A, and A minus as t minus applied to A, then I claim that these are the elements we are looking for. Well, indeed, they are self-adjoint because the functions t plus and t minus are real. They are positive by the spectral mapping theorem because our functions are non-negative. And the remaining properties, the algebraic, well, first of all, their difference, A plus and A minus is A, just because t minus, t plus, well, the difference of the functions, t plus and t minus, is the identity map on the real line. And finally, it's clear that the product of t plus and t minus is 0. And this implies that the product of a plus and a minus is 0. So this proves the existence of such a pair. Now let's prove the uniqueness. So suppose that we have two positive elements, A1 and A2, such that A is their difference, and such that the product of A1 and A2 is 0. And let's introduce the absolute value of A. So we define the absolute value of A to be A plus plus A minus. This is the notation is the notation comes from the fact that t plus plus t minus is the usual modulus function on the real line. And now let's do a little calculation. So A squared is A1 minus A2 squared. When we multiply A1 minus A2 by itself, by using the fact that the product of A1 and A2 is 0, we see that this is A1 squared plus A2 squared. And for the same reason, this equals A1 plus A2 squared. On the other hand, we can do the same trick for A plus and A minus. So this is A plus minus A minus squared. This equals A plus squared plus A minus squared. And eventually this is the modulus of A squared. Here we use the fact that the product of A plus and A minus is 0. If we now compare these results and we take the square root of this, then by the uniqueness of the square root, we conclude that the modulus of A is A1 plus A2. Of course, here we use the assumption that both the elements are positive. Well, they are positive because each of them is the sum of two positive elements. And we already know that the sum of two positive elements is positive. And that's it. So we know that A is A1 minus A2, and the modulus of A is A1 plus A2. So this implies that A1 is given by the following formula. And so A1 equals A plus. And similarly, A2 is given by the following formula. And therefore, it equals A minus. And this proves the uniqueness of such a pair. Okay, now we are ready to prove probably one of the most important results about positive elements. So we have the following theorem. For each element little a in our algebra A, the element A star A is positive. Well, historically, this result was not a theorem, but it was an axiom. That is, it was a part of the definition of a C-star algebra. However, from the very beginning, Gelfand and Naimer conjectured that probably this axiom is redundant, so it follows from other axioms of a C-star algebra. But they were not able to prove this, and this result was proved by Kaplanski only in the 1960s. That is about 20 years after the fundamental paper of Bliphant and Nymark on C-star algebras. The proof is not very hard, but it's a kind of a trick. Let's divide the proof into several lemmas. So lemma one, for each self-adjoint element x of our algebra, x squared is positive. The proof of lemma 1 is a simple application of the spectral mapping theorem. Just the function which takes t to t squared is non-negative. Okay. Now lemma 2. Lemma 2. For each element x in our algebra, the element x star x plus x star is positive. So we take our element x and let's write it in the following form. So x is y plus iz, where I and z are self-adjoint. So we know that this is always possible, and y and z are uniquely determined by x. And then x star equals y minus iz. And therefore, when we multiply them, we get that the product of x star and x equals y squared plus z squared plus I multiplied by yz minus zy. Okay, and now let's multiply them in the opposite order. So we multiply x by x star, and what we get is y squared plus z squared plus I multiplied by zy minus yz. Okay, and when we take the sum of these two elements, we see that the sum equals 2 multiplied by y squared plus z squared. And the remaining terms just cancel. And so this is positive by lemma 1. So this completes the proof of lemma 2. Okay, now lemma 3. Lemma 3. Lemma 3 is purely algebraic. It holds in any unital algebra. So suppose that A is a unital algebra. And little a and little b are arbitrary elements of A. I claim that the spectrum of AB is almost the same as the spectrum of BA. More exactly, if we add 0, then we have the following equality. To prove this result, let's first observe that actually it suffices to show the following. It suffices to show that 1 minus AB is invertible, if and only if 1 minus BA is invertible. Well, this is just because for each non-zero number lambda, AB minus lambda 1 can be written in the following form. And so everything is reduced to the invertibility of this element. Okay, so if we now assume that if 1 minus AB is invertible, and if we denote by C the inverse element to 1 minus AB, then a short computation shows that the element 1 plus BCA is the inverse of 1 minus BA. This is an elementary exercise for you. And formally, this completes the proof. Now, of course, the natural question is where this strange formula comes from. How could we guess this explicit formula for the inverse of 1 minus BA? And so perhaps the following informal explanation is appropriate. So let's try to write an explicit formula for 1 minus AB. Formally, this formula works only if our algebra is a Banach algebra and little a and little b are very small elements. Nevertheless, we have the following formula. We just write the usual progression: 1 plus AB plus AB squared, which is AB, plus AB cubed, which is AB, and so on. And this is our element C. And similarly, 1 minus BA inverse is 1 plus BA plus BA plus BA, and so on. And let's now write this in the following form. This is 1 plus B multiplied by something and multiplied by A. And the expression in brackets is the following. This is 1 plus AB plus AB, and so on. So this is our element C defined in the previous line. And that's it. So this informal manipulations show where the explicit formula for the inverse of 1 minus BA comes from. Okay, so anyway, we have proved lemma 3, and now we are ready to prove our theorem. Let's do it on a new page. So we let B denote our element A star A. And so we want to show that B is positive. Well, first of all, it's clear that B is self-adjoint. So we can write it in the form B equals B plus minus B minus, where B plus and B minus are as one of the previous propositions. So they are positive and their product is 0. They are positive and their product is 0. So we want to show that B minus is 0. To prove this, let X denote the product of A and B minus. So we are going to apply lemma 2 to this element X. So what can I say about X star X? X star X is B minus A star A B minus. And since A star A is B, this is B minus multiplied by B, and B is B plus minus B minus, and by B minus. Okay, now the product of B minus and B plus is 0, so this is minus B minus cubed. And this equality implies that the element minus X star X is positive. Okay, so let's now look at the product X star. And let's write this element in the following form. This is X star X plus X star plus minus X star X. Well, the formula is obviously true. Now, lemma 2 implies that this element is positive. This is our lemma 2. And it follows from the previous line that this element is also positive. And the sum of two positive elements is positive. So we conclude that X star is positive. And now we apply lemma 3. So the spectrum of AB equals the spectrum of BA after we add 0 to both sides of the formula. So this implies that the element X star X is also positive. But we already know that minus X star is positive. So these two facts together imply that X star X is 0. That is, B minus cubed is 0. And finally, we apply the cubical root function, and we conclude that B minus is 0. And this completes the proof. Okay. As a simple application of this result, we can now define the absolute value of any element in a C-star algebra. So we introduce the following notation. For each element literally in our algebra, we define the absolute value of A to be the square root of A star A. So A star A is positive, and we can take the square root. And it's immediate from the definition that the resulting element is positive. By the way, this notation is consistent with the functional calculus. So let's observe that if our element is self-adjoint, then the absolute value of A defined by the previous formula is the square root of A squared. And by the superposition property, this is nothing but the absolute value of T, where T is the identity map of the real line, applied to A. So in terms of our previous notation, this is A plus A minus. So in general, we see that our notation for the absolute value is consistent with the functional calculus in this sense. And as another application, we get the following useful characterization of positive elements. So we have the following corollary. The following properties of an element in our C-star algebra are equivalent. Property 1, A is positive. Property 2, there exists a positive element B such that A equals B squared. Property 3, there exists a self-adjoint element B such that A equals B squared. And finally, property 4, there exists an element B in our algebra such that A equals B star B. Well, indeed, this is immediate from our previous results because, well, 1 implies 2 because B is just the square root of A. It's clear that 2 implies 3 and 3 implies 4. And our previous theorem shows that 4 implies 1. Probably that's all I wanted to tell you about positive elements of C-star algebras. So our next strategic goal will be to apply C-star algebras to the spectral theory of linear operators on the Hilbert space. And today we will discuss only some very basic facts about operators between Hilbert spaces. So we'll discuss some facts on operators between Hilbert spaces. We start with some pure algebraic definitions. Suppose that we have two vector spaces, x and y. X and y are vector spaces over the complex numbers. We say that complex function f, the product of x and y, is a sesquilinear form so in Russian this is полуторалинейная форма. If the following two axioms are satisfied, first, f should be linear in the first variable, that is, we have the following identity. And second, f is antilinear in the second variable. So we have the following. So here, lambda bar and mu bar are just the complex conjugates of lambda and mu. One more definition. If we now have a complex valued function q on the vector space X, we say that q is a complex quadratic form, a complex quadratic form if q is the restriction of a sesquilinear form to the diagonal. That is, if there exists a sesquilinear form f on the product of x by itself, such that q is the restriction, such that q is the restriction of f to the diagonal. It's the following formula holds. So in this case, we say that q is associated to f, and we use the following notation. A nice property of sesquilinear forms is that the complex quadratic form q uniquely determines the form f. More exactly, we have the following proposition, which is called the polarization identity. If f is a sesquilinear form on the product of x by itself, then we have the following identity. Okay. Well, the proof is an elementary computation, so I'll leave it as an exercise for you. Actually, what is really important is not the formula itself, but the fact that this formula implies that f is uniquely determined by q. So we have the following corollary, corollary 1. if I have two sesquilinear forms f and g, then f equals g if and only if qf equals qg. In other words, a sesquilinear form is uniquely determined by its restriction to the diagonal. This is a very nice property of sesquilinear forms. By the way, for bilinear forms, a similar result fails. For example, we can take any skew-symmetric bilinear form, then the restriction of it to the diagonal is identically 0. And we cannot reconstruct the bilinear form from the restriction to the diagonal. But for sesquilinear forms, this is possible. Okay, let's now give one more definition. Suppose that we have an arbitrary sesquilinear form on the product of two vector spaces. A sesquilinear form. Then we define the joint of f by the following formula. So this will be a function of the product of y and x given by the following rule. So it's immediate from this formula that f star is also a sesquilinear form. If we now have a sesquilinear form defined on the product of x by itself, then we say that f is Hermitian if f equals f star. So explicitly, this means that f of yx equals f of xy complex conjugate. So this is an analog of symmetric bilinear forms. Well, a sesquilinear form can never be symmetric, of course, but it can be Hermitian. Here's one more corollary of the polarization identity, corollary 2. If we have a sesquilinear form, f on x, then such a form is Hermitian, even only if the associated complex quadratic form is real. And the proof is very easy. So by definition, f is Hermitian, even only if f equals f star. And by corollary 1, this is equivalent to the equality of the respective quadratic form, qf and qf star. And by definition, this means that f of xx equals f of xx complex conjugate for each x. which means precisely that f of x is real. And this completes the proof. Okay, let's now relate sesquilinear forms to linear operators between Hilbert spaces. So suppose we have two inner product spaces, H1 and H2, inner product spaces. So at this point, we don't require the completeness. So they are not necessarily complete. And suppose that we have a linear operator T from H1 to H2. Again, we don't assume that T is bounded. It's not necessarily bounded. And let's introduce some notation. We define the sesquilinear form Ft associated to T on the product of H1 and H2 as follows. Ft of xy equals the inner product of Tx and y. So clearly this is a sesquilinear form. And in the special case where H1 equals H2, we can introduce the respective quadratic form Qt on H. So this is just the quadratic form associated to Ft. That is Qt of x equals the inner product of Tx and x. So this is the respective complex quadratic form. These functions are useful because actually each of them, I mean Ft and Qt, each of them contains all the information about the operator. So we have the following simple result. Proposition. Suppose we have two linear operators S and T from H1 to H2. I claim that S equals T if and only if Fs equals Ft. And in the special case where H1 equals H2, if H1 equals H2, then S equals T, if and only if their quadratic forms are the same. Qs equals Qt. Well, the proof is very easy. To prove property 1, we may assume from the very beginning that one of the operators is 0. So we may assume that, say, S is 0. Otherwise, we just consider S minus T. So it's clear that if T is 0, then Ft is 0. And conversely, if Ft is 0, then for each x, the inner product of tx by itself is 0. And this obviously implies that t is 0. And so this proves part 1 of this proposition. And part 2 is immediate from part 1 and from a corollary of the polarization identity. So 2 follows from 1. And from corollary 1. So let's recall that corollary 1 says that 2 sesquilinear forms are the same, if and only if the restrictions to the diagonal are the same. Okay, so let's now relate sesquilinear forms to adjoint operators. Suppose that we have 2 Hilbert spaces now, H1 and H2 are Hilbert spaces. And let T be a bounded linear operator from H1 to H2. And we have the following simple result, proposition, which is essentially just an observation. The sesquilinear form associated to the joint operator T star equals the form Ft star, which is the adjoint of Ft. The proof is a short elementary computation, which I leave as an exercise for you. So this is immediate from the definition of the adjoint operator and of the adjoint sesquilinear form. And as a simple application of this formula, we get the following useful characterization of self-adjoint operators. Proposition. Suppose that H is a Hilbert space and that T is a bounded linear operator on H. I claim that T is self-adjoint if and only if the associated quadratic form of T is real. So, well, the left-to-right implication is almost obvious. So my point is that we have the right-to-left implication as well. And this is quite useful. And the proof is almost immediate from our previous results. Well, T equals T star, if and only if our operators have the same sesquilinear form, Ft equals Ft star. So by the previous proposition, this is the joint of Ft. So we see that T is self-adjoint if and only if Ft is Hermitian. But we already know, and this was, if I'm not mistaken, corollary 2, that a sesquilinear form is Hermitian if and only if the respective quadratic form is real. Qt is real. And this completes the proof. So an operator in Hilbert space is self-adjoint, even only if the corresponding quadratic form is real. And in conclusion, let's prove a useful characterization of positive operators on a Hilbert space. So we have the following result, a proposition. Let H be a Hilbert space, and let T be a bounded operator on H. Then the following conditions are equivalent. Condition 1, T is positive in the sense that it's a positive element of B of H. Second, there exists a Hilbert space, another Hilbert space H prime, and there exists a bounded operator S from H to H prime such that T equals S star S. And finally, property 3, the quadratic form associated to T is non-negative. Okay, to prove the result, we need two simple lemmas. Well, first of all, lemma 1. You have two Hilbert spaces, H1 and H2, and a bounded operator T from H1 to H2. Then the kernel of the adjoint operator T star is the orthogonal complement of the image of T, and the closure of the image of T is the orthogonal complement of the kernel of T star. The proof of lemma 1 is a simple exercise. Actually, we can just apply the standard duality theory and the Ries's representation theorem, which gives us a one-to-one correspondence between a Hilbert space and its dual. Or we can write it in a more elementary way, but anyway, this is very easy. So the first equality is almost immediate from the definition, and to get the second equality, we just take the orthogonal complements in the first equality. Okay, now lemma 2. Lemma 2. Suppose that H is a Hilbert space, and suppose that T is a self-adjoint operator on H. I claim that T is topologically injective, even only if T is surjective, even only if T is invertible. Well, actually, there are two simple ways of proving this lemma. The first way is just to apply the fundamental result about dual operators between Banach spaces. So we know that an operator between Banach spaces is topologically injective, if and only if the dual operator is surjective. And this gives us the result. Or we can do it in a more elementary way. We can apply lemma 1, and we observe that everything follows from the following equality. The closure of the image of T is the orthogonal complement of the kernel of T. Well, this formula gives us the result, because if we assume that T is topologically injective, then this in particular is injective, and this formula implies that the image of T is dense. But since it is topologically injective, its image is closed, and so we conclude that T is surjective. If we now assume that T is surjective, then this formula implies that the kernel of T is trivial, and so T is injective. So we see that T is both surjective and injective, so it is invertible. And of course, if T is invertible, then it is topologically injective. Okay, so this completes the proof of lemma 2. And now we are ready to prove our proposition. Well, 1 implies 2. This is clear because if T is positive, then we can let H prime equal H, and S, let S be the square root of T. And we clearly have 2, property 2. 2 implies 3 is also very easy. If T equals S star S, then the inner product of Tx and X is can be written as follows. So we take a star from left to right, and we get the following. And this is obviously non-negative. So the most interesting point is to show that 3 implies 1. So to show that if the quadratic form is non-negative, then the operator is positive. First of all, since this quadratic form is real, we conclude that T is self-adjoint. T is self-adjoint by the previous proposition. And now we have to show that the spectrum of T is non-negative. So actually, first of all, we recall the fact that the spectrum of T is real because it is self-adjoint. So now to show that T is positive, it remains to show, now we want to show that for each positive real number lambda, the operator T plus lambda 1 is invertible. And by lemma 2, it suffices to show that this operator is topologically injective. So we do the following simple computation. We apply our operator T plus lambda 1 to an arbitrary element X and calculate the inner product with X. Well, this is the inner product Tx and X plus lambda norm of X squared. And since the first summand is assumed to be non-negative, we conclude that this is greater than or equal to lambda norm of X squared. On the other hand, by the Cauchy-Bunyakovsky-Schwarz inequality. This number is less than or equal to norm of t plus lambda 1 x multiplied by the norm of x. And if we compare now these two inequalities and divide them by the norm of x, we get the following. The norm of t plus lambda 1 x is greater than or equal to lambda multiplied by the norm of x. So this inequality implies that our operator t plus lambda 1 is topologically injective. And by lemma 2, we conclude that this operator is invertible. And this completes the proof. So this implies that t is positive. Okay, so that's all for today. At the next lecture, we continue this discussion, and we introduce some special classes of operators between Hilbert spaces. So we discuss isometries, co-isometries, and so-called partial isometries. And then we apply these operators to the so-called polar decomposition of linear operators.